Good afternoon. My name is Marco Antonio Paredes. I'm a PhD candidate in material science. It's a pleasure to share with you the topic failure analysis of Inconel materials fabricated by laser powder bed fusion. And I would like to talk about introduction. The laser powder bed fusion LPBF is one of the most versatile metal AM techniques. In this process, the laser melts a metal powder followed by solidification of the metal to form the final product. The nickel-based superalloy Inconel 718 is frequently used in various high-temperature components due to its exceptional resistance to oxidation and creep. These components typically operate at temperatures below 650. However, in this case of the rocket engine or gas turbine disk is a modern jet engine, operating temperatures can exceed 700 degrees Celsius. However, the porosity is one of the main challenges in LPBF process and has a considerable impact upon fatigue properties of a bulk. The porosity can be easily introduced by almost all AM process parameters. In order to prevent a failure, it is important to be able to determine the position, direction, shape, and size of the pores to know the final density of the piece that was printed. The CT with combined geometry has been used for non-destructive inspection of materials since 1980. The CT offers a 3D imaging inspection illustrates the density of the sample, locates and defects and porosities with great precision. The aim of this work is to determine the porosity characteristics caused during the printing process with samples of Inconel 718 printed parts by means of CT. In that sense, the 3D analysis was performed before mechanical tests in order to determine the porosity characteristics and remaining. Then, determining the influence of temperature of mechanical tests in the size distribution of remaining porosity. Finally, the samples were observed using a scanning electron microscope. Now, I would like to talk about the process. The superalloy Inconel 718 was chosen. The LPBF technique was used to obtain a bars printed at 0 degrees when dimension of 112 by 28 by 16 millimeters. From these printed bars, ASTM A8 specimens were manufactured with a EDN machine. Sample of 2 by 2 by 2.5 millimeters are cut using a diamond cutter, which is used for characterization by means of CT. Mechanical tensile tests were then performed at room temperature, tensile tests at 650 degrees Celsius, and finally a creep test at 650 degrees Celsius. Each of the mechanical testing sample was then characterized by CT. Fractographs of Inconel 718 were obtained using a JOL model scanning electron microscope. The specimens were using a microtomograph 160 kilovolts and 800 images with an exposure time of 2 seconds to acquire a volume for a resolution of 2.5 cubic micrometers. From of this volume, the porosity analysis is carried out. Results: isolate pores with size lower than 40 micrometers were obtained of CT porosity distribution AP. Stress strain curves was carried out at 22 degrees Celsius, obtaining a yield strength of 763 megapascals and maximum stress of 1042 megapascal. Tensile tests carried out at 650 degrees Celsius, obtaining a yield strength of 657 megapascals and maximum stress at 806 megapascal. Creep tests were performed at 650 degrees Celsius with a load of 1.88 kilonewtons and a rupture time of 46 hours was obtained. The porosity distribution and a same imagings are added to the mechanical curves. As secondary cracks and pores can be observed where the crack surrounds the trace of the print deposit and a creep tracks. The porosity distribution shows an increase at diameter size from 77.71 micrometers in AP condition to 148 micrometers in a tension test at 650 degrees Celsius. Also, an increment in the number of pores for 694 in AP condition to 8,524 in a creep test at 650 degrees Celsius. Conclusions. Computed tomography coupled with SEM images allow for the determination of porosity, which in turn acts as stress concentrations and promotes the formation of cracks. An increase in pore size of 32.49% was found in the creep test with respect to the tension test at room temperature, as well as increase of 27.63% in the number of pores in the creep test with respect to the tension test at 650 degrees Celsius. In additional research is ongoing to determine the evolution of pores during the failure from the shape and quantity of pores. Thanks a lot, Marco.